Welcome students. In our today's online lecture of group theory, we continue our topic order of an element in a group. For example, let G be a group and A belongs to G, n is natural number, so that A raised to n is equal to E if and only if order of A divides n. So solution, let A raised to n is equal to E and order of A is equal to m. So here we show m divides n. So to show m divides n, we use that division algorithm. So by applying division algorithm on m and n, so if we divide n by m, then we get n is equal to m into q plus r, where r is the remainder satisfying the condition 0 less than or equal to r strictly less than m. So suppose this is equation number 1. So here we show r is equal to 0. So suppose that r is not equal to 0. So now r is equal to n minus m into q. So from that we have a raised to r is equal to a raised to n minus mq, that is equal to a raised to n into a raised to minus mq, or it is equal to a raised to n into a raised to m raised to minus q. But here we have a raised to n is equal to identity and order of a is equal to m. So we have a raised to m is also equal to identity. So this is equal to e into e raised to minus q, because e raised to n is equal to e and a raised to m is equal to e, as order of e is equal to m. So the right hand side is equal to e. So here a raised to r is equal to e. So from that we can say as r is greater than 0, order of A is less than or equal to R. That is, M is less than or equal to R, which is not possible because our R is less than M. Hence, we must have R is equal to 0. So, we put R is equal to 0 in equation 1. Then we get N is equal to M into Q. That is, we can say M divides N. So, from that we get order of A divides N. Now conversely, suppose that order of A divides n, we show A raised to n is equal to E. So order of A divides n. So therefore n is equal to order of A into k for some integer k. So therefore A raised to n is equal to A raised to order of A raised to k, that is equal to A raised to order of A raised to k, but A raised to order of A is equal to identity element. So this is equal to e raised to k, that is equal to e. So thus here we get A raised to n is equal to e. So thus we have the important result, that is for any natural number n, a raised to n is equal to e if and only if order of a divides n. Now next example, let G be a group and A and B belongs to G be such that AB is equal to BA. If order of A and order of B are relatively prime, then show that order of A into B is equal to order of A into order of B. So for that we have that previous result, that is whenever n is natural number, a raised to n is equal to e, then we have order of a divides n. So solution, so that order of a is equal to m and order of b is equal to n. So we have a raised to m is equal to e and b raised to n also equal to e. As they are relatively prime, we have GCD of m and n is equal to 1. Now we have a into b bracket raised to mn is nothing but equal to a raised to mn into b raised to mn, because we have a into b is equal to b into a. So this is equal to a raised to m raised to n into b raised to n raised to m. But a raised to m is equal to e, b raised to n is equal to e. So this is equal to e raised to n into e raised to m. So the right hand side becomes identity element. So a into b raised to mn is equal to e. So by this result we can say order of AB divides Mn. So here we get the result, that is order of AB divides Mn. Now let order of AB is equal to K. So as order of AB is equal to K, K is the smallest positive integer such that AB raised to K is equal to E. Order of AB is equal to K. So K divides Mn. So therefore we have, as a into b raised to k is equal to e, so we have a raised to k into b raised to k is equal to e. So therefore a raised to k is equal to e into b raised to k inverse, or it is equal to b raised to minus k. So here we get a raised to k is equal to b raised to minus k. Now take n power on both sides. So therefore a raised to k raised to n is equal to b raised to minus k raised to n. That is nothing but equal to b raised to n raised to minus k, but b raised to n is equal to identity element. So this is equal to e raised to minus k, that is equal to e. So from that we get a raised to kn is equal to e. So a raised to kn is equal to e. So by that result we have order of a divides kn. But order of a is equal to m, m divides kn. But here GCD of m and n is equal to 1. So therefore we can say m divides k. And similarly we can show n divides k. But again, as GCD of m and n is equal to 1, we can write mn divides k. So mn divides k, it means that mn divides order of AB, because order of AB is equal to k. So thus by equation 1 and 2, we can say order of AB is equal to m into n. But m is nothing but order of A, n is nothing but order of B. So therefore order of A into B is equal to order of A into order of B. Now next example, if G is group such that A square is equal to E for all A belongs to G, then show that G is abelian. So given that A square is equal to E for all A belongs to G, so therefore A into A is equal to E for all A belongs to G. Therefore, if we pre-multiply both sides by A inverse, then we get A inverse into A is equal to A inverse into E. So on the left hand side we have, by associative law, A inverse into A is equal to A inverse for all A belongs to G. But A inverse into A is identity element, so therefore E into A is equal to A inverse for all A belongs to G. So therefore we get A is equal to A inverse for all A belongs to G. Now let A and B belongs to G. Because G's group operation is binary, so A into B is also element of G. So A and B are elements of G. A into B is element of G. So therefore we have AB is equal to AB inverse, that is equal to, by reversal law of product, this is equal to B inverse into A inverse. But as A and B are elements of G, B inverse is equal to B and A inverse is equal to A. So this B inverse into A inverse is nothing but equal to BA. Thus here we get the result AB is equal to BA for all A and B belongs to G. So therefore we can say the given group G is an abelian group. Now next example, show that G is nothing but set containing elements 1 minus 1 I minus I, j minus j, k minus k is a group under multiplication with properties I into I is equal to j into j is equal to k into k, that is equal to minus 1, and I into j is equal to k, that is nothing but equal to minus j into I. Then j into k is equal to I, that is nothing but equal to minus k into j, and k into I is equal to j, that is equal to minus I into k. Also find order of every element of group G. Now we prepare a composition table or multiplication table with respect to that operation multiplication of that elements. So this is the composition table. Here the operation is multiplication. So by using these properties, we have prepared this multiplication table. So here all entries in the table are elements of G. So therefore, this operation multiplication is binary, and we know that multiplication operation on complex number is associative. Also, 1 is the identity element in that group G, and from the table we have 1 inverse is equal to 1, minus 1 inverse is minus 1, I inverse is minus I inverse is I, J inverse is minus J inverse is J, K inverse is minus K, and minus K inverse is K. So therefore, G with that operation multiplication is a group. Also, to find order of each element, we have to find the smallest positive integer n, such that a raised to n is equal to e, that is identity element, but here the identity element is equal to 1 for all a belongs to G. So now 1 raised to 1 is equal to 1, that is identity element. So from that we can say order of 1 is equal to 1. Minus 1 raised to 1 is minus 1, and minus 1 square is equal to 1, that is identity element. So here 2 is the smallest positive integer such that minus 1 raised to 2 is equal to 1. So order of minus 1 is equal to 2. Then we have I raised to 1 is equal to I square is minus 1, I cube is minus I, and I raised to 4 is equal to 1. That is 4 is the smallest positive integer such that I raised to 4 is equal to 1. So order of I is equal to 4. Also minus I raised to 1 is minus I square is minus 1, minus I cube is I, minus I raised to 4 is 1. So order of minus I is equal to 4. Similarly, we have order of j, order of minus j, order of k and order of minus k all are equal to 4. Then next example, in the group Z7 dash with operation multiplication modulo 7, find 3 bar square, 4 bar raised to minus 3, order of 3 bar and order of 4 bar. So we know that Z7 dash is nothing but equal to set containing elements 1 bar, 2 bar, 3 bar, 4 bar, 5 bar and 6 bar. So Z7 dash forms a group with respect to a binary operation multiplication modulo 7 with identity element 1 bar, and we have 1 bar inverse is 1 bar, 2 bar inverse is 4 bar, 3 bar inverse is 5 bar, 4 bar inverse is 2 bar, 5 bar inverse is 3 bar and 6 bar inverse is 6 bar. Because we have 1 bar into 1 bar with that operation multiplication modulo 7 is 1 bar, then 2 bar into 4 bar is 1 bar, 3 bar into 5 bar is also 1 bar and 6 bar into 6 bar with respect to that operation multiplication modulo 7 equal to 1 bar. Now 3 bar square is nothing but equal to 3 bar into 3 bar, that is 9 bar, but modulo 7 it is equal to 2 bar. Then 4 bar raised to minus 3 is nothing but equal to 4 bar inverse raised to 3, but our 4 bar inverse is nothing but 2 bar, so this is equal to 2 bar raised to 3, so it is 2 bar into 2 bar into 2 bar, that is 8 bar, but modulo 7 its value is 1 bar, so 4 bar raised to minus 3 is equal to 1 bar. Now to find order of 3 bar, we have 3 bar raised to 1 is 3 bar, 3 bar raised to 2 is 2 bar, 3 bar raised to 3 is 6 bar, 3 bar raised to 4 is equal to 4 bar, 3 bar raised to 5 is equal to 5 bar, and 3 bar raised to 6 is equal to 1 bar. By using this operation multiplication modulo 7, so 6 is the smallest positive integer such that 3 bar raised to 6 is equal to 1 bar. So therefore order of 3 bar is equal to 6. Then to find order of 4 bar, we have 4 bar raised to 1 is 4 bar, 4 bar raised to 2 that is 4 bar into 4 bar that is equal to 2 bar modulo 7. Then 4 bar raised to 3 is nothing but equal to 1 bar. So here 3 is the smallest positive integer such that 4 bar raised to 3 is equal to 1 bar. So therefore order of 4 bar is equal to 3. Now we have next example. In the group Z dash with operation multiplication modulo 8, find order of 3 bar and order of 5 bar. So we know that Z dash is nothing but equal to set containing elements 1 bar, 3 bar, 5 bar and 7 bar, and Z dash forms a group with respect to binary operation multiplication modulo 8 with an identity element 1 bar, and 1 bar inverse is 1 bar, 3 bar inverse is 3 bar, 5 bar inverse is 5 bar, 7 bar inverse is 7 bar. Because we have 1 bar into 1 bar is 1 bar modulo 8, then 3 bar into 3 bar is equal to 1 bar, 5 bar into 5 bar is 1 bar, and 7 bar into 7 bar is 1 bar. So here the operation is multiplication modulo 8. Now to find order of 3 bar, we know that 3 bar raised to 1 is 3 bar, and 3 bar raised to 2 is nothing but 3 bar into 3 bar modulo 8, its value is equal to 1 bar. So therefore order of 3 bar is equal to 2, because here 2 is the smallest positive integer such that 3 bar raised to 2 is equal to identity element. So therefore order of 3 bar is equal to 2. Also to find order of 5 bar, we have 5 bar raised to 1 is equal to 5 bar, 5 bar raised to 2 is equal to 5 bar into 5 bar modulo 8, so it is equal to 1 bar. Hence order of 5 bar is equal to 2. Now next example, what is the order of 11 bar in the group Z12 with operation addition modulo 12? So we know that Z12 is nothing but set containing elements 0 bar, 1 bar, 2 bar, 3 bar up to 11 bar. So it forms a group with respect to a binary operation addition modulo 12. To find order of 11 bar, we have to find the smallest positive integer n such that 11 bar raised to n is equal to 0 bar. So note that here operation is nothing but equal to addition modulo 12. So 11 bar raised to n is nothing but equal to n into 11 bar. So we have 11 bar raised to 1 is 11 bar. 11 bar raised to 2 is nothing but 11 bar plus 11 bar modulo 12. So its value is 10 bar. Then 11 bar raised to 3 is 11 bar plus 11 bar plus 11 bar. That is nothing but 33 bar. But modulo 12, its value is 9 bar. Also 11 bar raised to 4 is nothing but equal to 8 bar. Then 11 bar raised to 5 is nothing but equal to 7 bar. So and so on. So if we continue this, we get 11 bar raised to 12. That is nothing but equal to 11 bar 12 times with operation addition modulo 12. So this value is nothing but equal to 0 bar. So here 12 is the smallest positive integer such that 11 bar raised to 12 is equal to 0 bar. So here we can say order of 11 bar is equal to 12. So thank you. See you in the next lecture. Goodbye.